On May 10, 2025, the container ship MSC Antonia was navigating from Marsa Bashir to Jeddah port. A route it had almost certainly sailed before. 304 meters long. 7,000 containers. Experienced crew. Familiar waters. Somewhere during that transit, the ship's GPS receivers stopped tracking the real world. They were receiving signals, strong ones. The equipment was functioning exactly as designed. But those signals were coming from a transmitter on the ground, not from satellites in orbit. And they were telling the ship it was somewhere it was not. The Eliza shoals were not where the ship's systems said the shoals would be. No warning. No alarm. No dramatic failure. Just a 304-meter ship moving at speed onto a shoal that the chart said wasn't there. Because the chart overlay was tracking the wrong position. 3 independent intelligence firms, Windward, Polestar Global, and Marine Traffic, confirmed the same conclusion: deliberate GPS spoofing. This video is about what that means. Technically. Regulatory-wise. And for anyone working in maritime cybersecurity or IACS U26 compliance today. GPS spoofing is conceptually simple. A transmitter broadcasts fake satellite signals at higher power than the real ones. The ship's GNSS receiver, doing exactly what it was designed to do, locks onto the stronger signal and starts calculating position based on that data. The receiver isn't broken. It isn't being hacked in any traditional sense. It is functioning correctly. The input is the problem. Here's the sequence, as reconstructed from Polestar and Windward's post-incident analysis. First, spoofed signals overpower the real satellite data. The ship's calculated position drifts. Second, ECDIS, the electronic chart display that the officer of the watch navigates by, begins showing that false position on the chart. It has no way to know the data is false. Third, the ship navigates based on what ECDIS shows. Fourth, the Eliza shoals exist in the real world. They don't exist at the coordinates the ship believes it's at. And then, contact. Polestar's analysis found something important: the AIS transponder, which is also GPS fed, was broadcasting erratic positions consistent with spoofed data before the grounding. The signature was visible. It just wasn't recognized as a threat indicator. The data tells the story clearly. In the fourth quarter of 2024, average GPS position errors in the Red Sea region measured around 600 kilometers. By the first quarter of 2025, just 1 quarter later, that figure had reached 6,300 kilometers. That is a tenfold increase. In 3 months. And the MSC Antonia grounding occurred during that same period of accelerating interference. This is not a statistical anomaly. It is a trendline with a predictable endpoint. It's comfortable to frame this as a conflict zone issue. GPS spoofing near Jeddah, in a militarized waterway. It makes the threat feel geographically contained. It isn't. Windward's Q1 2025 data documented average GPS position errors in the Red Sea region, reaching 6,300 kilometers. That's a tenfold increase from 600 kilometers the previous quarter. In a single quarter. In June 2025, an escalation in the Persian Gulf disrupted over 3,000 vessels in 2 weeks. In February 2026, a spoofing event in the Strait of Hormuz affected over 1,100 vessels. In the first 24 hours. With spoofed signals placing ships over airports and near a nuclear power plant. The Strait of Hormuz carries approximately 20% of the world's oil. It is 33 kilometers wide at its narrowest point. A spoofing event at scale in that corridor is not a cybersecurity incident. It is a navigational mass casualty scenario. And the hardware that makes this possible? Commercially available. Widely discussed in security research circles. Entry-level spoofing capability at costs that put it within reach of non-state actors. The asymmetry between attack cost and consequence is extreme. I want to be direct about this because I see it misunderstood in compliance workshops. IACS UR E26 does not mandate GPS spoofing detection. What E26 does require, under its detection function, is the ability to detect anomalous events. On computer-based systems, monitor network traffic for unexpected activity and flag deviations from expected operational parameters. A spoofed GPS feed produces none of those signals. The GNSS receiver is functioning normally. The data it outputs is indistinguishable from genuine positioning data at the system level. ECDIS ingests it without error. The integrated bridge system accepts it without alarm. E26 was designed around the assumption that anomalies can be detected by monitoring the behavior of networked systems. GPS spoofing attacks the data that feeds those systems, not the systems themselves. It is an input-level attack on a compliance framework built to detect process-level anomalies. This is not a criticism of E26. It is a gap that the industry needs to understand clearly. Because treating E26 compliance as GPS spoofing protection is a dangerous misreading of what the regulation actually covers. When I'm engaged on an E26 compliance project at a shipyard, one of the most important questions I ask the design team is this: at what layer is the position data validated before it reaches ECDIS? In most current designs, the answer is, it isn't. The GNSS receiver feeds ECDIS. ECDIS feeds the autopilot and the officer of the watch. There is no cross-validation between any of these layers. And that single-path architecture is the gap that made the MSC Antonia grounding possible. A properly designed GNSS integrity architecture has 4 components. First, multi-constellation reception. A receiver pulling simultaneously from GPS, GLONASS, Galileo, and Beidou is significantly harder to spoof. The attacker must convincingly mimic signals from 4 independent satellite networks in precise coordination. Second, position cross-validation against independent sources. Radar-derived position, inertial navigation output, and GNSS position should be actively compared. A divergence beyond a defined threshold, say 0.1 nautical miles, should trigger an alert before ECDIS auto-updates. Third, rate of change sanity checks. The MSC Antonia's position jumped thousands of kilometers in spoofing event signatures. A simple velocity plausibility filter would catch the most egregious attack patterns at the system level. Fourth, and this is the biggest gap I find in practice, bridge team training. When radar position and GNSS position disagree, the instinct of most bridge teams is to assume radar error or chart discrepancy, not GPS spoofing. That instinct needs to be retrained. None of these measures are exotic. The obstacle is not technical. It's that they require conscious design intent. And that intent must be present during the E26 compliance conversation at the shipyard, not after the vessel is already trading. If you are working on E26 compliance right now, whether as a shipowner, technical superintendent, or shipyard consultant, here are 4 questions to pressure test your position. Question 1. Which computer-based systems on this vessel receive GNSS-derived data as input? ECDIS is obvious. But also, autopilot, AIS transponders, VSAT antenna tracking, dynamic positioning. Any bridge automation that uses position as a parameter. That is your GNSS dependency map. If you don't have it, you can't protect it. Question 2. Does your integrated bridge system cross-validate GNSS against radar or INS position? If the answer is, it has a RAIM alarm, that is not the same thing. RAIM detects signal quality degradation. It does not detect a high-quality spoofed signal. Question 3. What is the bridge team's documented procedure when navigation sensor sources diverge? If that procedure is not in your safety management system, it will be noticed at your first E26 relevant survey. Question 4. Are your GNSS receivers multi-constellation? If the vessel was designed before 2022, single constellation receivers are likely. Retrofitting is not trivial, but the risk calculus needs to be formally on record. Let me put the larger issue plainly. The Global Navigation Satellite System was designed in a world where the satellites were trusted authorities. No one was broadcasting signals designed to mimic them. No one needed to. That world no longer exists, not in the Red Sea, not in the Persian Gulf, and increasingly not in other waterways where geopolitical tensions run high. The industry's typical response pattern to a cyber incident is predictable. Incident occurs, analysis is published, awareness is raised, working groups are formed. Guidance is issued 18 to 36 months later. By the time comprehensive GNSS integrity requirements make it into mandatory survey criteria, how many more hulls will have touched ground? Let me close with specific recommendations by stakeholder group. For shipowners and technical superintendents, audit your GNSS dependency map across your fleet. Know which systems trust GPS-derived data without any cross-validation. Review your bridge team training materials. GNSS anomaly should be a trained response category, not an improvised one. And at your next class survey, raise multi-constellation receiver capability as a risk item even if it isn't yet mandatory. For shipyards and system integrators, bring the GNSS integrity discussion into preliminary design review. By the time you reach commissioning test procedures, changing the position cross-validation architecture is expensive. At preliminary design review, it is a conversation. For equipment manufacturers, the GNSS receiver is a computer-based system. Its security profile, including spoofing resistance, is part of your E27 documentation obligation. Class approved does not mean tested against active spoofing scenarios. Check your approval criteria. Then check again. The entire GNSS architecture was built on an implicit assumption that satellite signals are authoritative and uncontested. That assumption was valid for the first 3 decades of commercial maritime GNSS use. It is no longer valid across an increasing proportion of the world's strategic waterways. What happened to the MSC Antonia was entirely predictable. To anyone watching the Red Sea spoofing pattern from Q4 2024 onward, the data showed average position errors increasing tenfold in a single quarter. The conclusion that a vessel would eventually be placed on a shoal by a spoofed track was not a surprising prediction. It was a scheduled outcome. The gap between a compliance document and a bridge system that actually catches a spoofed position before it becomes a grounding. That gap is where the next incident is already forming. The Eliza shoals have been on charts for a very long time. The ship knew they were there. It just didn't know where the ship was. If you found this useful, subscribe, and share it with a colleague in ship design or fleet management. The full article with all sources is linked below. I'm Captain Paul. This is Ship Paul Jobs. Maritime 4.0.